Okay, good morning everybody. I hope everyone's having a wonderful day. So today I'm going to be talking about more stuff involving dynamic programming. So the example we're going to be seeing today is involving the 0-1 knapsack problem. So I've defined this problem previously when I was talking about the fractional knapsack problem. And I also gave you just a quick reminder last day at the end of class. But just as a reminder, remember I have n items. It's going to be some set I. And each one of the items has a profit and a weight. And I'm going to represent this with two arrays. These are going to be one indexed arrays. So they're indexed from 1 to n. 1 to n, my apologies. There'll be 1 to n. And there's also going to be this knapsack capacity, W. So the goal here is that we're going to output a knapsack, which is going to be a subset of the items, I prime, where the profit, if I sum up all the profits of the items in my knapsack, it is as large as possible. So I have to, when I have my knapsack, I can't exceed the knapsack capacity when I sum up the weights of the items that I put in my knapsack. And it also is the property that the items have to either go entirely in or they're left out. So that's what I mean here by xi is either 0 or 1. And remember, xi, when it's equal to 1, that just simply means the item is in my knapsack. When it's 0, it means the item isn't in the knapsack. So for the purposes of this lecture, I'm going to mostly focus on just thinking about the knapsack as a subset of the items. It's rather trivial to think about it as the array X I defined previously in the course. You just simply would go through all the items in this subset or this collection of items, and you would just simply examine each one, just determine what item it is. You could flip to xi to be 1 or 0 for your solution. So anyways, are there any questions about what 0 knapsack is just before we proceed? Because the fact that we know what the problem is formulated as really matters for this lecture. Okay, so if we're all good to go, I'm going to first establish for you that the 0-1 knapsack problem satisfies the principle of optimality. For abbreviation, I'm going to refer to the principle of optimality as POO. That just makes it a little easier to remember. And the thing that you need to be aware of when we talk about dynamic programming is that any problem that you wish to apply dynamic programming to has to satisfy the principle of optimality. So in a much more broader way of talking about the principle of optimality is the case that all of my optimal solutions can be expressed in terms of optimal solutions of sub-instances of that problem instance. So for example, in our case, if I'm able to remove one of the items from an optimal solution, whatever's left, when I consider the instance where I remove that item, everything that is in that optimal solution without that item would be an optimal solution for the instance where I don't have the item as part of my collection of items. So, and this will work its way down, all the way down until I say consider one item or two items or three items. And that's how we're going to use the dynamic programming to build an optimal solution bottom up. So when it comes to dynamic programming, there's kind of major steps once you have the principle of optimality. So there's kind of three main steps once you have the principle of optimality, and you're going to see that today. So once you have the principle of optimality, we're going to derive a recurrence relation that expresses the value of the optimal solution. So this will fall right out of this result here. So when we look at this proof, when I try proving this for you, the principle of optimality is going to just fall right out of it, okay? So a lot of the ideas you're going to see in this proof are going to pop up in my recurrence relation that I defined for the optimal solution values. Then on top of that, so the actual algorithm itself, the way I'm going to show it to you is it's going to actually compute the value of an optimal solution. And then there's a way that we can use the information that we tabulate in our table so that we can actually get the actual optimal solution, like the knapsack, this I prime I have over here. Okay, so that's going to be the game plan for today. So So that's generally the kind of strategy you employ when you use dynamic programming. So just remember, you cannot use dynamic programming unless this principle of optimality holds for that problem. And every single time you consider a problem, you need to consider if this is a property that that problem has. So let's try proving this. So just to give you an overall kind of game plan with this, some people like to lovingly call this technique cut and paste. So the way this is going to go down is I'm going to formulate for you an optimal solution in terms of the knapsack. And then what I'm going to do is I'm going to consider, for the sake of contradiction, some part of my optimal solution where I remove part of it, in this case remove one of the items, and I'm going to, for the sake of contradiction, assume that it isn't optimal. So that would imply there's a better answer with the instance where I have those items, where I remove the item in question. And then I'm going to, as the name suggests, I'm going to cut out my optimal by looking at it without the item, and I'm going to paste it into my argument, where I'm going to effectively show you that if I assume there was a better answer, then all I have to do is I just simply take what I had for my optimal less that one item, and I can add back in the item, and I can see, okay, if I compare whatever this hypothetical better answer is versus my assumed not as good answer, I end up actually with a better answer. That leads to a contradiction. So we're going to see how this cut and paste kind of approach goes with this. So the first thing I need to do is define the scope of this. So I'm going to assume we are given an arbitrary 0-1 knapsack instance. So I'm going to assume I'm given an arbitrary instance of the 0-1 knapsack problem. So I'm going to give it a name. So I'm going to suppose, I'm going to call it x tilde is going to be equal to x1 tilde, x2 tilde, x3 tilde, all the way up to xn tilde. I'm going to suppose that x tilde is optimal. Now, because I formulated in terms of the zeros and ones, I'm going to describe it in terms of items now. And this will be an easy way for me to get to my next step in the reasoning here. So very often with these types of proofs, the first thing you need to do is really say what the optimal solution looks like, and then try to use properties to help you. Okay, so here we go. This means there is an optimal set. There is an optimal set of items. There's an optimal set of items. I'll call it opt. And it's going to consist of each of the indices of the items. So it's going to be 1, 2, all the way up to n, such that the x tilde I is equal to 1. So whenever one of these values is 1, like I said over there, if it's equal to 1, that means I put the item in the knapsack. So this is just going to be a collection of items that are labeled by their indices. So when I look at say if I want the weight or the profit of a given item, I'm just talking about the index that would be sitting in these arrays here, okay? So what is this going to be? So I'm going to call the number of items that's in this set, I'm going to call it k, with k is equal to k items, where k is less than or equal to n. So I'm using these bars to denote the size of this set, so the cardinality of the set. So just think of it as the number of items that are sitting in here. So I'm just going to write down what the optimal profit and the total weight of this knapsack would be. then the total profit. And the total profit is, so I'll just use the definitions of what I talked about with the total profit. So it's going to be the sum over I is equal to 1 to n of pi x tilde I, which is going to be equal to the sum of each one, so over all of the item indices in set opt, pi. So this is going to just, remember, this is just me going through each one of these items that's in this set. So I'm just showing you that, yeah, these are me saying the exact same thing. And if I sum up over all of the weights, I apologize, I've run out of space down here. It's I is equal to 1 to n of wi x tilde I is simply going to be where I go over all of the items in my set opt. And we know this is at most W because it's an optimal solution. So it means it has to follow all the constraints of the problem, right? So that sum over there, just as a reminder, what I just said, so it goes from the sum is equal to I is equal to 1 to n of Wi times xi tilde. So all I'm doing is I'm giving names to things that relate to the optimal solution. Very often this is a crafty part of the proof so that I have some clever way of talking about pieces of the optimal solution. So now that I have some way of characterizing it in terms of the items, like I did over there at the beginning of this lecture, now I'm going to talk about the optimal where I remove an item. Okay? So is everybody okay with this so far? So I'm just giving names and you writing down some symbols to represent some of the things I've talked about with the optimal. So give me 2 thumbs up if we're all good so far. Okay, so I'm going to proceed over here. So now I'm going to give a name to one item in opt. So I'm going to say let lambda is going to be some item in opt. So for the principle of optimality to hold, what we're going to need to do, so for the principle of optimality to hold, we need to show that for each lambda in opt, items opt where I remove item lambda. So this is set minus. I'm not sure if I've used this notation before, but that's just me saying take away lambda from the set opt. Items opt set minus the set containing lambda is an optimal solution to a subinstance with capacity W prime, which is going to be equal to W minus W lambda. So remember, this is the weight of item lambda. So what I'm saying is we're going to consider some subinstance where the capacity is just going to be simply the new knapsack capacity I'm going to look at is when I have W prime, where I'm just going to take what I had originally. I remove this item from my solution. So I'm going to consider a subinstance where I have only the items less lambda, and the knapsack capacity is going to look like this. So that is So notice the way I'm going to write this next part is I'm going to give names to the items that are going to be in this new optimal solution. So I need to make sure I do that and do it very carefully because I don't know what those items exactly are. I just know that they're somewhere in this set oft, okay? So I'm going to give names to them. So that is, suppose we have a subsequence of assignments. So when I'm referring to these assignments, I'm talking about the xi values, 1 or 0. Either you put it in the knapsack or you don't put it in the knapsack. A subsequence of assignments, x1 prime, x2 prime, all the way up to xk minus 1 prime. Because remember, when I remove lambda, item lambda, now I have k minus 1 items, okay? So just keep that in mind. So I'll just say that here just for the sake of clarity. For a subinstance, with k minus 1 items, for k minus 1 items, where lambda is not included. Remember, I just removed 1 item, so that means that there's k minus 1 items. Let me just switch my marker here. So I'm also going to give names to the profits and weights, seeing as I've given names to these assignments. So here we go. Let the profits and weights, let the profits and weights be P prime 1, P prime 2, all the way up to P prime K minus 1, and W1 prime, W2 prime, all the way up to WK minus 1 prime, respectively. So again, I'm just giving names to things to make this a little easier to work out the argument here. So now this is where the contradiction is going to start coming up, okay? So remember, this is what I said earlier. This is like the big game plan. So I've just given names to everything to help us get through this argument, okay? So now here's where I'm going to, this is where the contradiction in my proof is going to pop up. So suppose, we'll see, suppose items opt without item lambda, is not an optimal solution. This marker's a little funky. Let's try a different marker. Let's try this one. Let's see if this one's any better. I mean, it probably is readable fine, but I like to make sure it's nice and clean for you. Is not an optimal solution. Oh, this is much better. Is not an optimal solution to this subinstance. To the subinstance. Then, what does that mean? Then there exists another assignment where I'm going to give those names. Y1, Y2, all the way up to Y, K minus 1. So these are just names for K minus 1 assignments of items. Which has larger profit. Right? That's what I said earlier, right? That all I'm doing is I'm saying, okay, well, if mine isn't an optimal in this stage, then that means there's a better answer somewhere. I'm calling those assignments Y1, Y2, Y3, and so on. Remember, there's K minus 1 of these items. So now, It's okay if I go over to this board. It makes things a little easier to argue out here. Okay. So let's proceed over here. You're going to see what I mean by this whole cut and paste thing that I'm referring to. So once you lay out all these terms and the names for everything, very often the idea is all I'm going to do is I'm just going to consider what happens when I just throw in that kth item and see what happens. I'm going to paste it right back in and see what happens. Now, if I were to write out the profits, now the sum from I is equal to 1 to k minus 1 for pi prime xi prime. So if I have this, we know that this is less than the sum from I is equal to 1 to k minus 1 of pi prime yi. So let's see here. So we got p, yeah, we're doing okay here. So we got pi prime yi. Now this is because of the assumption we made, right? It means that this answer is better than that one, which is part of our assumption. It's baked right in. Now this is true if and only if I just do the following. So I'll use the double arrows here just to make this a little easier for me to write this out. So it's just if and only if. All I'm going to do is I'm going to inject back in the kth item, which was lambda, and see what happens. So this is true if and only if from sum is equal to 1 to k minus 1 of pi prime xi prime. So that's just the same thing I had on the left side of the inequality. I'm going to shove right back in the profit for item lambda and its assignment for the optimal I had before. And now this is where we're going to have some problems. So sum is equal from I is equal to 1 to k minus 1 of pi prime yi. And then we say, okay, well, it's p lambda x lambda with the tilde. So I have a question for you. If I were to put in, I added that term over on that side. What could somebody tell me about this left side of this inequality? Could somebody tell me something interesting about the left side of that inequality? What is that? What's on the left side? What's sitting right here? Well, here, I'll just explain it here. So if but the sum from I is equal to 1 to k minus 1 of pi prime xi prime plus the profit of item lambda times x lambda tilde, this is actually just equal to this. It's the sum over all of the items of opt, removing item lambda, where I go through all the profits, like I did previously, plus p lambda x lambda tilde like this. But what's this? What's this? Can somebody now tell me what this is? That I've kind of spelt it out a little bit further. What is this? Well, think about it. This is all of the items without item lambda. This is the profit of item lambda when I put it into my optimal solution. So this is actually just the total profit of an optimal selection of the items, right? As I set up at the beginning of the proof. Which is the profit for opt. And now all I'm going to do is I'm going to say a bunch of nonsense now. So now I'm going to sum up all the profits, because I can rewrite this now as this. And I'm just going to shove it into this and see if it makes any sense. So I sum over all of the items again that are selected in this case, where I inserted in P lambda's profit over here. But what does this mean? Does this make any sense to anybody? Does this inequality make any sense? It's a bunch of nonsense, right? This inequality is just a whole bunch of nonsense. Because remember, this is the optimal profit for, this is opt's value, right? All I did is I shoved back in item lambda. That's what I mean by paste. I'm just going to put it back in and see what happens. But if I try to paste it here, well, okay, so what is this? Well, that clearly can't be better than that, right? Notice the strict inequality here. This is nonsense, right? Which is a contradiction. As opt is an optimal solution with k items. So now, with this being said, I'm going to leave a couple sentences just to elaborate on what this means in the notes. But essentially what it boils down to now is I've just showed you that, actually, let me just say it here. Thus, any opt without lambda is an optimal solution. To the subinstance with capacity W prime is equal to W minus W lambda. Therefore, the principle of optimality holds for 0-1 knapsack. And we're done. So this is the consequence of that contradiction argument that I've proposed. And, oops, I missed an E over here. Let's put that E back in. Therefore, see, I pasted it in, okay? And so, are there any questions about this proof? Because I'm going to now just take what I have essentially said in this proof, show you a recurrence relation, and then I'm going to give you the algorithm for computing this. And then with how much time we have, we're going to do a full example, okay? So the recurrence relation is going to be the more layman's way of approaching this proof, okay? So let me put it on over here. Actually, no, let's do it here. Let's do it here, because it's actually not that long. So the big thing is there's really two cases here that happen actually in this proof. So this proof tells you that if I have an optimal answer, that essentially if I either have an option, either I can include the item or I don't include an item. That seems to be a key part of the optimal solution in the way I argued things here, right? Notice that I shove back in the item, and it doesn't matter which one. It has to be an optimal one, though. But What is an optimal one? It's whichever one is the largest one at that time of the ones I've considered. And indeed, when we think about it, it's like either I include the item or I don't include the item. That's really what the justification behind this proof is, right? So either I insert the item or I don't, and based on that information, I can formulate a recurrence that looks something like this. So I'm gonna leave a little bit more details in the notes if you really just want to convince yourself that, okay, so what exactly does this all mean? So here's a recurrence. So I'm gonna have this formulated in the following way. So I'm going to have two variables here, I and WT. So WT is going to represent a capacity limit to my knapsack. Think of it like W. I is going to represent the number of items I'm including so far in the knapsack. So for example, when I make I is 1, that means I'm going to try to include item 1 in the knapsack. If it's I is 2, that means I'm going to include the first 2 items in the knapsack, or I'm going to try to at least. 3, I'm going to try to put the first 3 items in the knapsack. I'm going to introduce at each stage of this 1 new item. You'll notice in my proof it really doesn't matter what order you do them in, but for our algorithm it's really simple to just think about it as I'm going to include item 1, then I'm going to try considering 2 items, then 3, then 4, and so on. So that's what I is. It's going to represent the number of items we're going to consider. Each one is going to be indexed as in the order I prescribed earlier in the lecture. WT, this is your capacity limit. And you're going to see that there's some pieces of this that are going to remind you of what I wrote just previously. So there's going to be 2 cases here. So the first case is when I can't fit an item into the knapsack, meaning that its weight is too much. Now, if the weight of it is too much, what I do is I consider what the optimal profit was before I considered item I, okay? So remember, I'm trying to write the optimal value of an optimal knapsack in terms of itself, okay? So if I can't fit item I in, then most certainly, if I were to recursively think about the first I minus 1 items with the same weight capacity. So if it is in the case that WI is in fact larger than the weight capacity, so my knapsack capacity here, you're not going to put item I in. So this translates to do not. So don't put in item I, okay? That's what this case is saying. Now, here's the other possibility. So I'm going to check amongst 2 possibilities. Either when I include item I, do I get a better knapsack by putting it in or by not putting it in? So when I put it in, what I have to do is I need to decrement the amount of weight that I'm going to contribute by doing that. But what is that expressed as? It's actually expressed as a subinstance. And in fact, it's the exact same one that's in this proof. So your choices either are don't put the item in or put it in. And you take the better of those 2 answers. So this is just simply where you find out that, oh yeah, not putting item I in is better. Or you have it where you put in item I. And something in this second one should remind you of the proof. So if I could fit item I in, there's only 2 things that can happen. So the second case is try to put I in. You pick the best option. Note that technically the first possibility here contracts into the first case. You'll see this in the algorithm when the way I write this. So it's just simply saying in the first possibility, don't put I in. The second possibility is you put I in. So just to be clear, in the second possibility, what you're doing is you're considering the optimal profit when you consider the first I minus 1 items. And then what you do is when you put that item in, you have to decrement the amount of weight for including item I in. So that means when you're looking at your, so you're going to see in a moment what I mean by this, but essentially you can actually write all of these vals, this table out, and based on that, you'll see that I can actually look up the values of previous optimums for certain sub-instances. In this case, this is the one that's exactly in the proof. This is the one where I decrement off, say in my proof I had called it lambda. So when I get rid of item lambda, I'm considering this sub-instance where I consider the first I minus 1 items without lambda in it. So all I'm doing is I'm shoving lambda in, just like I did actually here in this proof. So these are the two possibilities. So you're going to see how I'm going to use these, okay? So let me just give you kind of the idea first, then I'll write out some pseudocode, and then we'll do an example, okay? So if you're wondering about more details around this, I'm going to have some more details in the notes if you need some more just to kind of explain the setup for this. Okay, so let's proceed. So you might ask, Dan, what do you do with all these vals, this thing I call val over there? So here's what you do. Now, you notice that I didn't actually give you any base conditions for this recurrence, right? Notice that I didn't say anything about, okay, well, what are the smallest values here in certain cases? Believe it or not, there's actually base cases for this recurrence. But remember, this recurrence's job is to represent the value of an optimal solution. So let me just describe for you the definition of the two base cases here. So if I tell you that it's val 0 WT, so this is going to just be equal to 0. And this is over all of the values for WT. So WT can range from 0 up to W. And naturally, you're going to have it where you consider, say, your items, but you have no capacity limit. So, sorry, you have a capacity limit, it's 0. If that's the case, how many items can you even put in the knapsack if the knapsack capacity is 0? Just hypothetically speaking. Now, in our problem formulation, it's a positive number, but say if I told you the knapsack capacity was 0, can you put any items in it, in the knapsack? No, right? Yeah, exactly, you can't. So that's why the value here is 0. So this is the case for if you range this over all of, so this is over all of the items. So now when I have this, what I can do is I can arrange all of my values now into a table. So a two-dimensional array that looks like this. Val 0, 0, val 0, 1. Val 0, W minus 1, val 0, W. So I'm going to build a table that's going to consist of rows and columns that are they're going to compute out this recurrence. But notice the way it's written, it's always in terms of smaller instances of my knapsack instance. Val 1, 1. Val W minus 1, val 1 W. So I'll explain what each entry of this exactly means, but it goes all the way down until you have val N 0, val n1, val n w minus 1, and then we have val nw. So this is going to be the table that our algorithm is going to generate. And we're going to generate it reading off each one of the rows and working our way down. But we need to initially set up the table so that all of the first column also has zeros in it, as the base case here. And then all of the first row is going to consist of zeros. And then we're going to build bottom up the value for the optimal profit. So this is going to be your 2D array or table that our algorithm is going to build. By the way, what are the dimensions of this table? Can somebody tell me? This is going to be an important part of the analysis. What are the dimensions of this? So notice this goes from 0 all the way down to, all the way up to n. And it goes 0 all the way up to w along the columns. So notice that I start at 0, so the dimension is always going to be 1 higher in this case than n and w. So notice I'm going to have w plus 1, and here I'm going to have n plus 1. This is going to be relevant for the analysis for this algorithm, because we have to make this table. And if I tell you it takes constant time to construct each entry in this table, you can see quite quickly what the running time of this algorithm is going to look like, right? So let's proceed. So actually, I have a question for you. Where is the optimal profit in this table? Can somebody tell me? Where is the optimal profit? So if I look at what my recurrence was telling me, remember, each one of the rows is me saying, I'm going to introduce another item in. This bottom row means I'm considering all n items. As I go along the columns, this is me saying, I'm going to increase my knapsack capacity limit by 1 in each one of my columns. Here is when the knapsack capacity is in fact W. So what entry has the optimal profit in it? So if I look at this table, what has the optimal profit sitting right in it? This is going to be a very important part of the algorithm. So if it helps at all, think of this instead of it as a top-down process. So suppose I were to tell you, okay, if I put these parameters into val, if I were to think about this as a recursive algorithm where I computed the recurrence relation over there, what values should be sitting in there? So think about, instead of bottom up, think of it as top down, if it helps. I'll give you a hint. It's actually sitting right here. So this entry actually has the optimal profit sitting in it. Because remember what this entry represents. It's saying, after I've considered all n items with knapsack capacity W, this is in fact going to be the optimal profit for such an instance. So that is going to be the value for the optimal profit. Now, believe it or not, the algorithm is essentially me just walking you through this process of building this table. So I'm just going to omit talking about the pseudocode. It's going to be in the notes. I'll tell you that the running time for this algorithm, is based entirely on the construction of this table. And I told you the dimensions are n plus 1 and w plus 1. And when you compute the optimal profit, you're going to end up with a running time that looks like nw. It's entirely dictated by the dimensions of this table. That's very common in dynamic programming, by the way. So why don't we do an example and see how we compute this out, okay? So I'm going to try to blast through an example here. So I apologize if I'm going to need a couple more minutes, okay? I was hoping I could get this done a little sooner, but the proof, we had to take a little bit more time. So I'm going to leave in the, actually, maybe when we come back, we'll talk about collecting up. Let's just try to let's try to do this. Let's try to do this. I'll put more details in the notes about how we collect up the items, but I want to make sure that we see a proper example of doing this. So there's going to be more details in the notes when it comes to this. One thing I must stress is that the running time of this algorithm is very suspect. It's very strange. I'll talk more about what I mean about this actually when we talk about this on Monday, and then I'll move to another topic. So it's actually a very important technical detail. So I'll talk more about that weird NW over there that comes right out of the construction of this algorithm. So here's the idea. So let me just give us an instance, and then we will build up. So suppose, let's have an example. And suppose I have five items. Item 1, item 2, item 3, item 4, and item 5. I'm going to have WI, so all my weights and profits. I'm going to have 6, 5, 4, 2, and 2. And for the profits, I'm going to have 6, 3, 5, 4, 6. And I'm going to have the knapsack capacity be equal to 10. So I have 5 items, and I have the knapsack capacity being 10. So what I'm going to do in the algorithm is I'm going to build this table, the one I just described over there. So here we go. So because the knapsack capacity is 10, I'm going to have 11 columns. 0, 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. And so these are going to be my J values on the columns. On the rows, I'm going to have I values that are going to go 0, 1, 2, 3, 4, 5, because I have 5 items. Now, I gave you the base conditions of the recurrence relation, which those are going to be the ones that they'll get expressed as for loops in the algorithm itself. It's really nice and straightforward. So all I'm going to do is I'm going to start by entering in the first row. It's a whole bunch of zeros, because that's what the base case of the recurrence tells me to do. And I'm going to fill in the first column with all zeros here. Now, we're going to have to be very careful here. So I'm hoping this won't take too long, okay? So what we now have to do is we have to consider each of those val entries that I had over there. So remember, this is going to be a 2-dimensional array. And each one of my entries represents, so for example, when I look at this entry right here, I'm asking you if I consider item 1, so I'm looking at this column here. When I consider item 1 where the knapsack capacity were supposedly 1, what would be the optimal profit in this case? So what you do is you use the recurrence relation to tell you this. So notice in this case that if I look at this entry and I ask, okay, well, what's the weight of item 1? It's 6. So notice that we fall into the case where I do not put item I into the knapsack, because the knapsack's capacity is going to get exceeded in this case because it's 1 and my weight is 6. So most certainly I can't fit it in. So you know all of these entries are all going to be 0 up to this stage. And then I can put in item 1. So all you do when you do this is you simply say, okay, well, your choices are either the one directly above it, or I look in the entry where I have one less item I'm considering. So in this case, I have no items, where the capacity 6 minus the weight, in this case it's 6 minus 6. So I'm comparing this value plus the profit of item 1 versus this on its own, vanilla. That's it. So I pick that entry plus 6 or 0. Which one wins? It will be 6, right? And notice that I only have one item, so all of these are going to end up being 6s. So similar idea is going to be applied here. Notice that the weight here for, now I'm considering item 1 and item 2 at the same time. So now I consider the second item here. Notice its weight is 5. So notice that I'm still going to have a whole bunch of zeros just sitting right here up until I get to 5, because there's no way I can fit item 2 with weight 5 into this knapsack, right? So that's going to fall into the case where you do not put in item I, in this case, item 2. So here we go. So your choices now are either for this entry, the one directly above it, which is 0, or it is simply this capacity limit minus the weight of that item, which is 5, so this entry, plus the profit of that entry for item 2. In this case, okay, well, 3 versus 0, you end up with 3. And now you're going to have some choices here. So notice that I have the limit 6. So now here in this entry, I have the choice of either picking the one directly above it, 6, or I have, okay, so it's either I'm going to try putting I in. So my choices are either I just take item 1, or I'm just going to see if I can get something better. So notice here I have knapsack capacity 6. So I have 6 minus the weight of item 2, which is just going to be 1. So it's 0 plus 3 or 6. In this case, 6 wins, and it's going to win always in the rest of these entries. And then you consider this next row, and you would keep doing this. So notice that here, notice that the weight of this one is 4. So you know these are all going to be 0 because there's most certainly no way I can fit that in. So everybody get the general idea here? Because I generally all you're doing is you just look at the entry directly above it. You compare that against what would be the entry directly above it, left shifted over towards wherever that entry would be. If I put that item in, that means I'm going to decrease the weight I have. Just like in my previous examples here. So those are your 2 entries in this table you always have to keep in mind when you're filling this in. So when I proceed doing this, what happens is I end up having the option where I could put 5, 5, 6, 6, 6. I think it's 8, and then 11. I'll fill in a bit more of this, and we'll look at one more entry just to make sure we're clear what we do with this. So we have 0. In this case, I'm able to put in the item 4 a little earlier on. Its profit is 4. 5, 5, 9, 9. Let's look at this entry. So notice here that I'm looking at item 4 right now. So my choices right now are either 6, or I look at what's the weight of item 4? The weight of item 4 is 2, right? So I'm going to take 8 subtract 2, which is going to be 6. So I take 6 plus the profit of item 4, which is just 4. So it's 6 versus 10 in this case. So I'm going to take the 10. And it works this way too in this entry as well. Here you're allowed to do a little bit more. But essentially boils down to this: 6, 6, 10, 10, 11, 11, 11. Sorry, 11, 11, 15. My apologies. 15, 15, and 16. So if somebody asked you what the optimal profit is, it's going to be sitting right here. So you tell me that the optimal profit is 16. But I didn't tell you how to get the items. So because of the sake of time, and I apologize for going longer here, I just really have to show you this. What I'll do is next day, I will show you how you could get the items, but I'm going to include in the notes how you get the items. So if you want to work on that problem, you can work right ahead. When I get back, I'll walk you through this process. Okay, everybody? I apologize for going longer here today. So I'll show you that process, and I'll show you what's strange about that running time next time. Okay, everybody? So I say thank you very much, and have yourself a beautiful day. And have a good weekend too. I'll see you later.